Hello，能听见吗，杰哥？
哎，可
喂，
以，可以，可以，你能听到我
哦，
吗？
我能听见，我刚才不小心点错了，反正正好也没来几个人吧。
好的，好的，我现在还有点事儿，我把你设主持人吧，四
啊，
号
你
还没上来。
好好好，
哦，我看到他了，稍等啊，我把拉进来。
嗯，你给我设成主持人，我就可以看见那个等候室了。
好，那我就点你啊。
嗯，好，
OK，
其他人
那个
都，
四行我也把他设成联系主持人了。
卢世航，你不要点全部进来，现在你没到时间的时候不要点，听见了吗？卢世航，你那边没有麦吗？好，好，那你就先不要那个，待会儿那个什么，待会儿等他们那个到点了再全部放进来，现在先不要，好吧？嗯，我看一下你这个行不行啊？你怎么把 WCM 放进来了？这不用放啊，这早就已经搞完了。那是 ComMag 8月1号截稿，WCM 我们已经前几天让你们审的不就 WCM 吗？没事儿，我给你删掉了。好像没别的了吧？唉，行，我先闭一下麦，然后等会儿可能恨可会来，你先稍微等一下啊。Hello, Hank.
Hi, can you hear me?
Hi, hi, Hank.
Hi, fine. Yes. Good
Yeah, yeah,
afternoon.
you
Good
can see
evening.
me, right? Okay,
Yeah, yeah,
great.
sure. Okay.
Hi, Fabiola.
Hello
How are you?
everyone. fine. Yourself?
Yeah, so we still have 9 minutes to go. So let's test the internet. So Henk, can you please share your screen and let's see whether we can see your. I think I shall make you the co-host.
Yeah, you need to enable it.
Okay. And yeah, now I can. Yeah, I can see the screen. Can you turn your pages? See if it can. Yeah. Great. Yeah, okay.
Perfect.
Okay, so Fabiola, can you?
Yes, I can do the same. Can you see my slides?
Yeah, very clear. Okay, perfect.
Okay.
Yeah. Okay, then let's wait for 8 minutes and then we will start. So I will first briefly introduce you and then I will cue you. You can then start your presentation. So Henk will be the first and then Fabiola.
Right,
That's
and we
great.
have 45 minutes, right, for the talk, and then 15 minutes Q&A. Is that correct?
My
Not
presentation is about 50.
Not so strictly. You can have 50 minutes talk, and then you can left 10 minutes for the Q&A,
Okay.
depending on how many people will ask questions.
Yeah, sure.
Yeah.
And how do people ask questions? They ask live or they do through the chat? What's the procedure?
I will ask them to enter into the chat, and when during the Q&A, I will name the questioners, and he will ask in live. Yeah.
Okay, sounds good.
So Henk, I have just sent you an email about our special issue.
Always giving me work, yeah.
Sorry.
No. I will take care of it tomorrow.
Yes. Thanks for the support, Henk, and also Fabiola, for our events. So how are your summer holidays? Are you taking a vacation?
Hopefully, in 2 weeks.
In 2 weeks. Oh, great.
Yeah.
So you will travel around?
Yes, I'm supposed to go to Iceland this year.
Ah, nice.
Quite cold there because in Rome they are almost melting. So.
How about you, Henk?
In Sweden, in the Nordic countries, the vacations are almost over. So I think after next week, everybody comes back to work. So it's
okay.
Not so like in Italy, where it's in August, I guess, the main vacation.
So I heard from Wymeersch that you recently got sick.
Yeah, I got COVID 2 weeks ago. It was
COVID.
Very painful. But the worst thing is not being able to smell and taste. That was awful.
Are you now recovered from your?
Yeah, like 80%, but still, it's like when I smell coffee, I cannot smell 100% coffee. You know, it's very sad. Yeah.
That is totally sad for an Italian guy, especially.
No, you feel really depressed. You feel you don't crave anything anymore. It just everything tastes the same. Wine, it's sad. How about you, Fan? You have time for vacation?
Maybe also next, so maybe early next month. Yeah, always have lots of stuff to do, you know. So
Yes.
lots of so you know that book chapters and this magazine special issue. Yeah.
Yeah, always busy. But it's okay. You're young, right? So you can handle it.
Yeah. So far so good. But we should collaborate again, right? So
Yeah.
last co-author paper.
Yes. Exactly. But yeah, it is really busy, so it's always difficult to find time.
Yeah. Actually, we recently have done lots of works on the vehicular stuff. Yeah, so maybe you will be interested, and we can maybe set a call to discuss. Yeah.
Yes. I guess from China you guys still cannot travel, right?
Yeah, we're not able to travel abroad now. So you guys are very fortunate. You can travel to all kinds of conferences now, right?
No, but it's very sad. I have lots of Chinese students. They haven't been home in 2 years. It's
oh, really?
yeah, really tragic.
But I think they can travel to Sweden, but it will be difficult for them to go back to China.
Yeah, that's the hard part. Yeah, they're stuck in quarantine for a long time.
Yes. How about you, Fabiola? Do you have any Chinese students?
I was supposed to have, because some of them wrote me just to visit our research group, but then it was impossible due to the COVID pandemic. So it was very sad, because I was in contact with 2 or 3 very good students according to their CV. So I was very excited to receive them in our lab, but unfortunately it was not possible. So I hope that will be possible in the next future.
Yeah, I think the policies will be released, I believe, to maybe next year. Yeah, I always want to travel. I missed all the conferences, the ICC GlobalCon, MICAS, Radar conferences, all of them, for almost 3 years. Yeah.
ICC was pretty close, no? In Seoul, not too far from China.
Yeah, but still, you need to be quarantined for like 3 weeks. You go back to China.
Yeah.
And then, yeah.
It's a long time.
Very high cost.
Yes. Yeah, sure. Hopefully, next year will be better.
Yeah, hopefully. Okay, I'll share my screen now and okay, now we have 50 people waiting in the waiting room. So let's wait for another 2 minutes and then we can start.
Sure. By the way, when will the video be live on YouTube? How long does that take?
We're trying to do live streaming on YouTube, but in China that is not very viable. So we now stream in a Chinese Chinese website, the Bilibili.
Okay.
Yeah. Okay, so I think people are all in now. So Shihang, can you please mute all? Okay, let me mute. Okay, I think now it's time for us to begin. And okay, so Shihang, you can see my screen, right? I think. Yeah. So Shihang, please mute all the people, and then. Okay. Okay. So. Welcome everyone to the IEEE ComSoc SPS webinar series, and this is our 2nd season, and this is a 5th seminar, and which is also the last seminar of this season. And today we are very honored to have Professor Henk Wymeersch and Professor Fabiola Colone as our guest speakers. So I will give a brief introduction first to Professor Henk. Okay, so before the formal introduction, I would like to call for papers. There are two, there's one special issue and one a symposium on integrated sensing and communication. The first one is the IEEE ComMag feature topic on integrating sensing into communications in multifunctional networks, which has a deadline of August. And the second one is the third IEEE International Symposium on GSNS, so on joint communication sensing, deadline October 17th. So you're more than welcome to submit your works to this special issue and this symposium. Sorry. Okay, and so our first speaker will be Professor Henk Wymeersch. So Henk Wymeersch obtained his PhD degree in electrical engineering, applied sciences in 2005 from Ghent University, Belgium. He's currently a professor of communication systems at the Chalmers University of Technology, Sweden. He's also a distinguished research associate with Eddie Alban University of Technology. Prior to joining Chalmers, he was a postdoctoral research with the MIT. So Professor Wymeersch served as associate editor of IEEE Communications Letters, IEEE Transactions on Wireless Communications, and IEEE Transactions on Communications. And he's currently a senior member of the IEEE Signal Processing Magazine editorial board. And during the 2019 and 2021, he was an IEEE distinguished lecturer with the Vehicular Technology Society. His current research interests include the convergence of communication sensing in the 5G and beyond 5G context. Okay, before we start the first seminar, I would like to remind you about our Q&A rules. So all the audiences will be muted during the seminar, and please do not annotate on your screen because everyone can see your annotation. And also please type your questions and send them to the host and co-host, and we will collect questions from both audiences from Zoom and offsite live broadcasting. During the Q&A, we will choose 3 to 5 questions to ask a speaker. And you will be named and you are encouraged to ask questions by yourself. Okay, so far that's all the introduction for Henk's seminar. And now I will hand over to Professor Henk Wymeersch. So Henk, the screen is yours.
Right. Perfect. Let's see. Good. Can you confirm that you can see the screen in the correct mode?
Yeah, I can see it.
Perfect. Okay. Thank you, Fan, for the introduction, and also to IEEE ComSoc and Signal Processing Society for the invitation to present this work. So this presentation relates to ISAC in the sense that it's on radio localization, mainly, also a little bit on radio sensing in 5G and beyond. So first of all, let's go into a little bit of motivation. Why do we need radio localization in 6G? And this is really motivated by a number of very difficult use cases that have been defined for 6G. And the use cases that I present here are from the HexaX project, so where you can see at least part of the URL, hexax.eu, which is a European flagship project that aims to define a vision of 6G in Europe. And as part of this project, we are contributing towards defining use cases and requirements for those use cases. So here are just 3 selected use cases from HexaX. The first one is infrastructure-less and embedded networks. So where, for instance, you would have cooperative localization between vehicles, which has a high requirement of localization accuracy, for instance, 1 centimeter accuracy, with a relatively high update rate and high availability and high scalability requirements. Another application is, for instance, augmented reality, where you need maybe even less than 1 centimeter localization accuracy, very high orientation accuracy as well, high update rate, and again, high availability. And a third example use case is robot and cobot interaction, so where robots are mutually interacting or interacting with humans, where again you have very high requirements on localization accuracy as well as velocity resolution and update rate. And these example use cases cannot be met by 5G. And this really motivates the research towards 6G in order to try to meet the requirements for these selected use cases, or at least go towards them. So with this motivation in mind, let's look at what we believe 6G will bring for localization and sensing. So this figure here shows on the horizontal axis localization uncertainty, ranging from 1 centimeter to 100 meter, and on the y-axis different deployment environments, indoors, urban outdoors, and rural outdoors. And then you see these different colored blobs, they represent different technologies. So for instance, you see GNSS, which can provide wide varieties of uncertainty depending on the variation of GNSS, but mainly for rural outdoor scenarios. If you go to urban indoor scenarios, you can use ultra-wideband 4G or 5G to go down to meter level accuracy. And this can support some of the traditional applications, but not those very strict applications I talked about in the previous slide. So for those, we probably would need 6G. And then here I put this green colored blob on the performance of 6G, which will provide centimeter level accuracy indoors and in urban outdoor scenarios. And the question is, why and how can 6G provide this? So we will talk a little bit about the underlying technologies of why we believe 6G can provide this high accuracy for these scenarios. So with this motivation, let's now go to the outline of this presentation. So I will first talk a little bit about the foundations of radio localization and sensing. Since this is mainly an ISAC audience, I thought it was good to talk a little bit about the differences between localization and sensing. Then I will talk about how localization works in 5G, both what is done in practice and what can be done with 5G as it is, with little modification. And then I will talk about integrated sensing, localization, and communication towards 6G. I know that the common term is ISAC, integrated sensing and communication, but I think localization is really an important part of that. So maybe ISLAC could be an alternative word for this. And then I will end with just with one slide with some main research questions and challenges. All right, but let's start about talking about the foundations. So this figure here is a slide that I use also in my wireless communication course at Chalmers, where we show on the top left a source emitting a wideband waveform towards a receiver, and if the signal can be cleaned up enough and the signal is sufficiently wideband, then the received waveform would look like something like on the right, whereas you see on the x-axis time with very high resolution, so this is nanosecond scale, and on the y-axis the received signal amplitude. And what you see is that in the beginning you just have noise, and at some point the signal arrives, and that would probably be the line of sight or direct path, and then you see all these resolved multipath components until in the end you only have noise. And now for position, typically you only care about this line of sight path because it tells you something about distance, but presumably all of these other multipath components, they relate to something in the environment, so they can be used for sensing, but maybe also for positioning. Now, in reality, a normal receiver would not have access to such high resolution measurement, but we use different kinds of measurements, such as signal strength, time-based measurements, and angle-based measurements, which I will talk about in a minute. Now, given these measurements, then to figure out the position is a standard statistical estimation problem, which means that we can rely on all the traditional tools from estimation theory to solve this problem. This includes Fisher information theory for performance analysis and signal design, algorithms such as geometric algorithms, as well as maximum likelihood algorithms, as well as methods based on convex optimization and Bayesian filtering. A lot of work is done also on signal optimization, which here there's a distinction between signal optimization for communication and for localization. So for instance, the directional signals that you would use for high SNR communication are not the ones that actually you would use for positioning. I will talk more about that later. And then we need to deal with all kinds of practical considerations such as synchronization, calibration, hardware limitations, and so forth. And now the nice thing about radio-based positioning and also sensing to some extent is that we can rely on the continuous developments in communication, and they each present an opportunity for positioning. So over the years, there's been, of course, the introduction of MIMO, millimeter wave, massive MIMO, now terahertz, intelligent surfaces, and so forth. And each of these, we can then think about how can we reuse them for positioning. Now, I use the terms localization and positioning interchangeably, but let me just make a little bit these terms explicit just to be clear. So when I talk about positioning, positioning is a term that really comes from wireless communication and refers to the 3D, to estimating the 3D location of a connected device, a user equipment or UE. Localization instead has been used mainly by the robotics community, which refers to estimating the 6D pose of a robot. And here the 6D corresponds to the 3D position and the 3D orientation of a robot. And then in localization, we kind of borrow that term from the robotics community and then use it also for what we traditionally called positioning, so 3D localization of a user device. So again, I will use positioning and localization interchangeably. Some people have more strict definitions, but this is how I reason here. Sensing now, on the picture on the right, I show different kinds of sensors. So there's many types of sensing that you can do, ranging here from the top left from humidity sensor to alcohol sensing. Sensing in general, in a typical kind of dictionary definition, refers to the detection of events or changes in the environment. Now, if I limit this to wireless communication, sensing itself has also been used, for instance, like RF sensing and carrier sensing. Now, when I think about ISAC, the more normal word, the more normal meaning of sensing is more radar type sensing, monostatic and bistatic sensing, which refers to estimating ranges, angles, and Dopplers. And this is really where sensing and localization connect, because for localization, we would also estimate ranges and angles, and in some cases, Doppler as well. So now let's go back to the different kind of measurements that we would use for positioning, but conceivably also for sensing. So the first kind of measurement is signal strength, and the use for signal strength is mainly comes from the path loss equation, right, where you see that on this equation that received power decays with distance according to this simple mathematical equation. And then if you measure a received power, conceivably you could invert it and recover the distance. Now in practice this doesn't work, because this is really shown on the picture on the right, where you see that for each distance there's a wide variety of received powers that you could have. This means that this mapping is not one-to-one. And for that reason, using received signal strength for estimating distances is very dangerous. It's something nice you can do in theory in a paper, but it will rarely work in practice. And for that reason, signal strength is most commonly combined with fingerprints, where in each location there's a unique fingerprint of signal strength from different access points. And this fingerprint is unique to that location, so the signal strength can be used to then recover the location. The most common measurement for positioning is time-based measurements. So I will not go through all of the equations for a reason of time, but just look at the picture on the right. So where a source is emitting a signal, for instance, a base station, the signal takes some time to travel over the air and then arrives at the receiver. And then the receiver, in this simple line of sight scenario, would estimate the time of arrival of that waveform. And this time of arrival would depend on the distance over the speed of light. So that's how long it takes to go over the air. But you also must account for the clock bias, because the transmitter and receiver do not necessarily need to be synchronized, at least not to the level needed for positioning. So for that reason, the estimated time of arrival would be the distance over the speed of light plus a clock bias. And this is the clock bias of the user device. And this means in positioning, you need to solve also for this clock bias. And this also happens, for instance, in GNSS. The equations on the right show a typical OFDM version of this, so where you have a received waveform that depends on a channel gain, transmitted waveform, and then a kind of delay steering vector where you see a linear increase of phase across subcarriers. And then you can estimate delays by just doing an FFT and looking at the peaks. Something similar happens with angles, so you can estimate angles of arrival or angle of departure. On the left side I show how angle of arrival works. So you have here a remote source, let's say a mobile phone, with a single antenna emitting a signal. This arrives at the base station, who's in far field of the transmitter. The base station is equipped with, in this case, a linear array with lambda over 2 spacing. And then because of this angle of arrival theta, the signal arrives a little bit later at successive elements, which translates to a phase change. So then the observation model at the base station would be a channel gain, and then a steering vector that depends on the angle of arrival plus noise. And in this steering vector, you see the linear increase of the phase with the antenna index, and which depends on the angle of arrival. And again, you have a similar structure as you had with delays. You can do an FFT, look at peaks, and then you can measure the angle of arrival. A little bit more or a little bit less intuitive is angle of departure. So in this case, the base station would emit signals across all of its antennas. So it would have a vector of signals across the antennas. And then the remote user would see a scalar waveform if the user has only a single antenna, which would be a complex channel gain, the same steering vector, but now transposed times the transmitted waveform plus noise. And from this waveform, if the receiver samples it, you can have discrete time observations. And if you connect enough of those discrete time observations, you can estimate the angle of departure. And of course, for this angle of departure to be meaningful, you need to know the orientation of the base station, because if you rotate the base station, the angle of departure will change. How this is done in practice is by sending directional beams. So the base station would send directional beams in different directions. The user could measure the signal strength, and then the beam with the highest signal strength would then be directly mapped to the corresponding angle of departure. An angle of departure in this case is a very valuable measurement because it constrains the user to be on the line away from the base station. And then you can put those measurements together in different ways. So if you do only delay-based positioning with time difference of arrival measurements, you constrain the user to lie on the intersection of hyperbola. If you do based on round-trip time measurements, where you measure directly the distance based on a back and forth signal, then the user is constrained to be in the intersection of a number of circles. If you do angle-based positioning, the user is constrained to lie on the intersection of lines in 2D or 3D, and then you can do any combination of the above. Of course, these measurements are typically subject to noise and biases, so these intersections, for instance, of circles is not perfect. And in that case, you would formulate the positioning problem as a statistical estimation problem, where you have a vector of measurements, y, a bunch of angles or delays, which relate to the hidden state, so the position of the user, maybe the clock bias, the orientation of the user, through some deterministic mapping, which you know, plus measurement noise. And then you can apply, for instance, least square estimation or maximum likelihood estimation to recover x from y. And now these kind of problems are typically very nasty non-convex problems, so you would solve them by first having a pre-processing to have an initial guess, and then you would do gradient descent on this cost function or on the maximum likelihood cost function. So this is just the basics of how positioning works. Now let's see how this maps into what is done in 5G. So the standard approach for positioning in 5G is using time difference of arrival. And here I show how this works in uplink. So you have a user emitting a signal to several base stations. These base stations are perfectly time synchronized, so they completely agree on the time. This means that when base station I measures the time of arrival at base station I would be the distance between the user and the base station over the speed of light, plus the clock bias of the user plus noise. And this clock bias, again, you don't know. Now, to get rid of this clock bias, you would take differential measurements. So you would declare one of the base stations to be the reference base station, and then you have these differential measurements, which no longer depend on the bias. And each of these differential measurements is a difference of distances, which geometrically corresponds to a hyperbola. This is what's shown on the right. You have 3 base stations here, and then one of them is the reference base station. You can compute then 2 time difference of arrival measurements, and then you must lie on the intersection of these hyperbola. Now, the nice thing is that time difference of arrival, at least in uplink, you can do it with 1 transmission per device. So it scales really well. On the downside, it is limited, first of all, by the base station placement. So the base station needs to be in a good configuration to have good positioning accuracy. If they're all on a line, that would probably not be good. And then you're also limited by bandwidth and multipath. And the bandwidth and multipath limitation, they really mean that the hyperbola are not beautiful geometric hyperbola, but they're kind of blurred. Right? And how blurred they are really depends on how much bandwidth resolution you have and how much multipath you have in your environment. Since release 16 of 3GPP, there's been several enhancements to positioning. So you can do now uplink and downlink time difference of arrival. You can do multi-base station round-trip time measurements. This is similar to, for instance, how ultra-wideband works, where you send from the user to the base station sends a reply, and then you measure the round-trip time. So you never need to estimate the clock bias. You can do downlink angle of departure or uplink angle of arrival. So there's no, for instance, uplink angle of departure, because typically the user will not use angular measurements because it only has few antennas. There's also been lots of work in standardization on the positioning signals. So this here is in time frequency, how the positioning reference signals would look like. So you would have orthogonal signals for the different base stations, but that would in total span a large time frequency range. You need a large frequency range to have good delay resolution, and you need a kind of sufficient time range to have enough integrated SNR. And then you can adjust the duration of these positioning reference signals based on the application. And then you can combine these positioning reference signals with directional beams. So that's what's shown here on the picture on the right, where the base station is sending directional beams in different directions successively. And for each of those beams, it would use this time frequency pilot pattern, which would allow the user to estimate the signal strength, which gives an indication of the direction, as well as the channel frequency response for that direction. Doing this, according to at least the work in standardization, you can get sub-meter accuracy, but you need very dense deployments of base station, and you need this perfect synchronization between the base stations. And when I say perfect, I mean basically sub-nanosecond synchronization errors. And this is because 1 nanosecond in delay converts to 30 centimeters in ranging error, and that is then leads us to a combination of such errors leads to high positioning errors. Another limitation right now is that typically, even though you have potentially a lot of base station antennas, the beams that are being used are still quite broad. So this limits the angle resolution, and also typically you have very limited knowledge of the beam patterns at the base station, which prevents you from using very high resolution processing. But I think now in standardization, this is being appreciated as a very important topic, and a lot of work is ongoing on refining both positioning protocols, algorithms, and signals, as well as architectures. And now this is also being extended to sensing in release 18. And I can refer to this paper that appeared recently in Communication Magazine on how positioning 5G works, if you want to know more information. Now, within 5G, there are several things that you could do, but that are not being done without any real change to standards. So the first one is to do multipath exploitation. So traditionally, multipath is something that harms you. It interferes with the line of sight path. It creates ambiguities. But in fact, if you have both angle measurements at the base station and at the user side, you can exploit a multipath. And the reason for this is kind of a very simple counting argument. So if you look at this figure here on the right, you have a base station, and here I do localization with a single base station. You have a user which has an unknown position, maybe an unknown heading. Now, if the user has an antenna array, I need to also estimate the heading of the user, of course. And then there's a propagation environment with different objects. So for instance, if I have a large reflecting wall here, then I can associate with this wall a so-called virtual anchor. So that's the reflection of the base station with respect to the wall. And then when the user is moving, the incidence point of the wave on the wall is moving, but the virtual anchor is always in a fixed location. And when I connect the virtual anchor with the user, I go through the incidence point. All right, this is just to say that with each multipath component, I have three-dimensional unknowns. Right? So this could be the incidence point location, this is 3 unknowns, or it could be the virtual anchor location, also 3 unknowns. However, at the same time, I have more than 3 measurements, because with each path that I receive at the user, I can have 5 measurements. And I have 5 because I have the delay of the path, the time of arrival. I have the angle of departure at the base station in azimuth and elevation, and I have the angle of arrival at the user in azimuth and elevation, provided I have a planar array. So this means that I have more observations than unknowns, and that means that actually the multipath can help you. So for instance, in this case, it turns out that you can localize yourself with a single base station if you have one resolvable multipath component, and you have the angles and delays of that multipath component. So that means you only need one base station, and all the synchronization problems that you had, they go away. Similarly, you could even think about removing the line of sight component, so the grid line, if that is gone, if the line of sight is blocked for whatever reason, but you have sufficient resolvable multipath, you can still solve the localization problem. I think in this case you need 3 non-line of sight multipath components. So multipath can really be our friend if it is resolvable. And this is really what you would do in sensing, right? You would try to sense the environment to figure out where the multipath components are, but we reuse them directly for improving the positioning. Now, what you can also get as a byproduct, of course, is you can figure out where those incidence points are, and then this allows you to map the environment, to create a 3D map of the propagation environment, and which then could be used by the next user going into the environment. And the nice thing is, of course, that the synchronization problem, as I mentioned, is gone. It is solved by nature because the wall is somehow by nature synchronized to the base station. If you want to know more, here are 2 of our papers where they talk about how to do snapshot and tracking localization for this scenario. I think I also have a very short movie on this, so where a user is moving around the base station, and as it is moving, it is trying to figure out where it is, and at the same time mapping the environment in terms of large surfaces, scatter points, and also there's kind of dots appearing here. These are clutter, so these are kind of things that are appearing but just for a short time and then disappearing, and then the filter needs to take care of that. Another thing that you could do with 5G right now, but it is not being done, is to do per user signal optimization. So as I mentioned before, how 5G right now works is you have these directional beams, and then within each directional beam you would do this time frequency positioning reference signal, but this is hardly optimal. This is because if you already know more or less where the user is, you shouldn't spend energy in illuminating areas where you know the user is not. And if you have some prior information, you can actually do much better signal design. And this is kind of spatial signal design, which is of course also relevant for sensing applications. You can do this by doing a Kramer-Rao bound optimization, which you can solve as a convex optimization problem. And then you would get results as shown on the right. So let's look, for instance, at the figure on the top right. So this is seen from the base station. If you want to illuminate towards a user and you know the angle interval of where the user is, and you want to help the user estimate the angle of arrival, then what you would do intuitively is to beam as much energy to the user as possible. And it turns out by doing this optimal pre-coding design, this is exactly the kind of signal that you would design. However, if you want to now consider a more challenging scenario where the user is again in the same angular range, but the user only has a single antenna and wants to estimate the angle of departure, then sending a directional beam towards the user is actually the worst thing that you can do. It cannot estimate angle of departure with just one directional beam. You should send a diversity of beams with lots of ripples, and this helps the user to estimate the angle of departure. And this is visualized with these beams here. So they are beams with lots of ripples. They have lots of side lobes. That's just a side effect of the beam design, but these turn out to be optimal for angle of departure optimization. And these are very different from the beams that you would use for communication. It turns out that those beams actually have a nice relation to the so-called sum and difference beams that have been used in radar, where you have an additional power allocation on top of those beams. And what we found is, well, and you can see this in these papers listed here below, is by using optimal precoders at base stations, you can have significantly improved positioning performance, not just for the direct line of sight path, but also if you know where an obstacle is, you can illuminate both and have a relative power allocation to optimize positioning performance. It turns out you can also do this with analog arrays, so you don't need digital arrays to make these very fancy beam patterns, even like the ones shown here in the colorful pictures in the middle. Analog arrays can do this as well with some additional computation. However, it turns out that doing this optimization of this beam codebooks tends to be high complexity, so probably you want to use a codebook-based solution rather than doing on-the-fly optimization. Let me just take a sip of water. And then a third potential, and okay, I'm preaching to the choir here, of course, is to use sensing within 5G. So you can think of having a full duplex transmitter which communicates to a receiver, but at the same time uses the backscattered signal to do radar kind of signal processing. And now at high frequencies where you have these large bandwidth and large arrays available, the backscattered signals can provide good information about range and angle, and this really acts like a radar. So the picture on the top right, if I put FMCW, then it would just be radar, but if you use, for instance, OFDM, then the backscattered signal could also be used for radar processing, but the forward signal would then be used for communication. And this then allows you to play lots of interesting games, and of course there's lots of work in the ISAC literature on this. You can play these games in time, frequency, and space to have performance trade-offs between radar and communication. So here, in the figure on the right is an example of a work that we did where we do OFDM power allocation. So we just have single antenna transmitter, single antenna receiver, and then the backscattered signal. So all we can play around with is the power allocation. And we know, of course, that if we just care about communication, the optimal power allocation would be water filling, and that corresponds to this point on the right, where on the x-axis we show the capacity, so a communication metric, and on the y-axis the range CRB, so a radar metric where lower values are better. So if we do standard water filling, that's the best for communication, but actually turns out to be the worst for radar. And then if we do the best kind of power allocation for radar, that turns out to be kind of really bad for communication, but very good for radar. And we have this Pareto optimal frontier that we can walk on using these optimization tools. So this is just one example of how you could play with power. You can, of course, play with beamforming, combining, and so forth. On the other hand, to my understanding, you cannot have all the full freedom that you would have in normal radar. For instance, if you have a MIMO radar with virtual arrays and orthogonal waveforms, you cannot do that when you do communication at the same time. But nevertheless, I think that this potential is the foundation of what ISAC is all about. So the integration of sensing and communication by doing monostatic radar with communication signals. All right, so this is was so far a little bit about how 5G positioning works and what we could do with 5G with minimal changes. But now let's look a bit more forward and see what 6G will all be about and how it will help localization and sensing. Now, if we look at 6G, and I don't pretend to know what 6G will be, but Chalmers is part of several European projects where we try to define 6G, so at least I can give some indication of what is kind of agreed among the consortium partners of what 6G will entail. So 6G, first of all, will have a variety of carrier frequencies. There's a lot of talk about terahertz. I don't think really frequencies above 1 terahertz will be used for 6G. Maybe we go to higher millimeter wave frequencies of 140 gigahertz, but they will be combined with the traditional millimeter wave frequencies and also sub 6 gigahertz. And I think we should not forget that all of these frequencies together will make up 6G. It's not just the high frequencies. And all of these play a role for positioning and also for sensing. Of course, by going to these higher frequencies, we'll have large aggregate bandwidths, far above 1 gigahertz. People are talking about 10 gigahertz of bandwidth at 140 gigahertz. And this high bandwidth is really good for positioning because it provides us high delay resolution. And that, of course, is also very good for sensing, both monostatic and bistatic sensing. Because we will work at higher frequencies, we'll, of course, have to deal with higher path loss, which then we must mitigate by having a large number of antennas, not just at the base station or access point, but also at the user. So we imagine that at the user device, you will have an array or even several arrays on the user. And this means that if you want to do positioning and if you want to do even beamforming towards a base station, you need to know the orientation of the device. And this means that we go from 3D positioning to 6D positioning in 6G, unavoidably. In 6G, now sidelink is again on the table and as a topic of standardization. This provides us with means to do relative positioning, so bistatic sensing, for instance, between vehicles. And of course, it's going to be used for radar as a monostatic sensing. I think a very interesting development again, which has been talked about for many decades now, but maybe now it will really become reality in 6G. Then the fifth topic that I think will be part of 6G is, of course, network densification. Working at these higher frequencies, you need many more access points, and this will, of course, lead to having higher probability of line of sight to those access points. So even though I said you could do positioning without the line of sight pad necessarily, by having line of sight, it really helps you. And a very nice example of this is distributed cell-free massive MIMO, where you would have many access points per user. And I see great potential for massive MIMO, even at of cell-free massive MIMO, even at lower frequencies, to provide higher resolution. At low frequencies, you don't have much bandwidth, so you cannot have good delay resolution. You don't have large antenna arrays, so you don't have good angle resolution, but by having a phase coherent cell-free massive MIMO system, you have basically a very large aperture and you are always operating in near field. And this provides an additional kind of resolution, which is something that I think we should really exploit as a community. The sixth topic is the integration of sensing, localization, and communication, as I mentioned already. So there's a lot of work on ISAC, but localization will be an important part of that, not just the sensing by itself. If we know where a user is, we can beam energy towards that user, and that's a localization problem, not just a sensing problem. The seventh aspect is that there will be more emphasis on data-driven solution using artificial intelligence and machine learning, not for every problem, but for kind of several interesting and hard problems. And then the eighth and last bullet is that we will have the ability to shape the environment with intelligent surfaces. So these reconfigurable intelligent surfaces can help us direct signals in certain directions, which will improve localization sensing, not just communication. With all of these comes challenges, and I don't pretend to know all of the challenges, but the ones that I'm aware of that are really plaguing our research is, first of all, the hardware impairments, which are, I think, much more severe for localization than for communication. Because for communication, you care mainly about the end-to-end channel, while for localization, you care about each individual component of the channel. What are all the angles, delays, and Dopplers? And then the last bullet is something that is often forgotten, which is that if you want to have this extreme performance of centimeter level accuracy for positioning and sensing, then you need extreme calibration as well. You need to know exactly where your base station is. You need to know exactly the tilt of the panels of your base station and so forth. And it is very difficult to achieve that. Of course, I didn't come up with all these topics by myself. This is the outcome of several, for instance, European projects in this case, such as RISE-6G, HexAx, Reindeer, Locus, and Ariadne. And I refer you to all of these to see more of the kind of enablers and challenges. And if you want to know more, here are one of the deliverables in HexaX project, as well as a recent tutorial paper on 6G localization. All right, and I could talk about each of these for 10 minutes or more, but I will not do that in the interest of time. I will just talk about data-driven solutions using artificial intelligence, and as finally on the use of reconfigurable intelligence services for localization. So if you think about the use of AI, one of the big topics in recent years was so-called end-to-end learning for communication. So this is what is shown on the figure on the top. So you have a message S that you want to send from a transmitter over a channel to the receiver. So on the channel you put X, you get Y as an output, and then the receiver needs to decode the message to get S hat. And of course, for the last 50, 60 years, we've been building transmitters and receivers of different degrees of complexity. And the goal of end-to-end learning is to say, let's just throw away, or to some extent, throw away the transmitter and the receiver that we know and just replace it by neural networks. And these neural networks could be just unstructured, but they could also have a structure that mimics the traditional transmitter and receiver. This is called model-inspired AI. And then we could learn this transmitter and receiver end-to-end. And this is especially good when you don't have a good model, right? Or when the model-based methods that exist, they're not really working really well. And an example that I think is really nice, for instance, of a channel is a nonlinear fiber channel. So this is far away from wireless communication, but a nonlinear fiber channel is very, very complex. It includes linear and nonlinear components as well as noise. And it is really not known what is the optimal receiver. So you could have a model of the channel, but not have a good receiver. And in that case, doing end-to-end AI-based learning could help you find what is the optimal constellation for this channel, what is the optimal encoder, and what is the corresponding optimal receiver. And now to train the transmitter receiver, you would need an end-to-end loss function. It's typically the cross entropy loss. And here are some examples of figures of results where they show that, okay, the end-to-end learning AI-based transceiver can perform the same or better compared to the model-based transceiver. But interestingly, up to last year, there's been very few works on how to extend this to, for instance, integrated sensing and communication. So here we want to just present one potential way of dealing with this problem from an ISAC perspective. So the model that I will deal with is somehow the most simple model that you can think of in this context, where there's a transmitter and a co-located receiver. The transmitter is sending messages to a remote communication receiver, which must decode a message. At the same time, the transmitter wants to figure out if there's a target in the environment and where is this target. Okay, so the transmitter, by looking at the backscattered signal, must figure out the presence of a target as well as the target state. So in this scenario, there are two channels. There's the communication channel from the transmitter to the communication receiver, which depends on the message M, how the message is encoded across the antennas Y, and then the transmit array and the channel gain. At the same time, you have the the radar channel. Here there are two options. So if there's no target, then the radar received signal would just be noise. In the case there is a target, then the radar received signal would be the noise plus the transmitted signal that is then received back at the receiver times the complex channel gain. And if in case there is a target, of course, then the goal is to estimate the angle towards this target. And of course, this problem is so simple, you could develop a model-based solution to this, but we will get to that later. So how you would then encode this in an autoencoder would be as follows. You would have an encoder at the transmitter that would take the message and convert it to a constellation point. The transmitter would also have a beamformer that would take prior knowledge that you have of where the communication receiver is and where the target is, and then convert this to a beamformer. You combine then the beamformer with the message to have the transmitted signal Y. This signal then goes over the radar channel and at the same time over the communication channel, so that you have the communication signal received at the communication receiver, which must then apply another neural network to recover the communication message. And then the radar observation goes to 3 neural networks, one to determine whether there's a target, one to determine the angle to the target, and one to determine a measure of uncertainty about this angle. How sure are we that the angle is really this value? And these are the standard outputs that you would want from a radar receiver, right? Presence, the estimate, and how sure you are of this estimate. Well, for the communication, you just care about the message. And it's important to note that the receiver for the radar is actually co-located with the transmitter. So the radar receiver knows what is the transmitted message. Okay, now the main challenge then in this kind of scenario is how do you define the loss function? And what we did is we decomposed the loss function to several parts. You have the communication loss function, which is just the cross entropy loss. For the sensing capabilities, we have three terms. We have the cross entropy loss, again, to determine whether a target is present or not. So here T denotes a target being present or not, and Q determines whether we think a target is present or not. Then we have, for the regression, mean square error loss on the angle. And then we have a Gaussian pre-log term to penalize overconfidence. And together, this is called the negative log likelihood function. And this is a very natural loss function for the radar problem. And then we combine the two. So we have the communication loss function and the radar loss function with a linear term, which tells us how much do we care about radar and how much do we care about communication. Okay, and then let's look at some results. So here are some results with on the x-axis on the left, detection probability versus symbol error rate. And this is in a case where the radar target is in one angular sector and the communication receiver is in another angular sector. And we see that with end-to-end learning, we can do as good as a kind of optimized model-based baseline. On the figure on the middle, we show the radar RMSE versus symbol error rate. And again, we have this trade-off. And we can do pretty much as good as the optimal baseline, which is model-based. And on the figure on the right, we show the learned waveforms for different values of this omega r, so how much we care about radar. So in blue, if we only care about radar, we only design a beam that illuminates the target. If we only care about communication, we have in red a beam that only illuminates the communication receiver. And then in green is when we have a trade-off between radar and communication. And now, even though we can achieve as good as a model-based baseline, you may ask yourself, who cares, right? Because then you would use the model-based baseline. So what happens is that things become interesting when you add, for instance, hard disturbances, for instance, hardware impairments. What if the array antenna spacing is not exactly lambda over 2, but there's some very small perturbations? If the model-based algorithm does not know about those perturbations, then it will be affected. And this is what we show in the figures here. So on the left is detection probability of the radar versus symbol error rate. The end-to-end learning is in green, and then the model-based baseline, which is not aware of these perturbations, of course, is severely degraded. And the same you see on the figure on the right, where you have root mean square error versus symbol error rate. The end-to-end learning does really well, but with the model-based approach, you have a severe penalty just because the model-based baseline is not aware of the antenna perturbations. And I think in general, hardware impairment is a good use case of AI-based methods. All right, in the last few minutes, I will just talk about the use of reconfigurable intelligent surfaces towards 6G localization. I believe many of you know about reconfigurable intelligent surfaces. I will not talk too much about the basics. So they comprise a lot of small so-called meta elements, which are controllable through phase or delay. And this allows you to send a so-called unnatural reflection to an arbitrary direction. And this allows, for instance, to overcome line-of-sight blockages. When the line of sight between a transmitter and receiver is blocked, you can use a large intelligent surface to have a directional beam towards the receiver and somehow overcome the line-of-sight blockage. There's lots of benefits for localization and sensing. So for instance, you can do localization with line-of-sight blockage. And if the intelligent surface is really large, there's a good chance you're in the near field of the intelligent surface, and then you can use the wavefront curvature for improving positioning. We had a paper now 2 years ago on radio localization and sensing with reconfigurable intelligent surfaces, where you can see more kind of the capabilities of RIS in this context. So let's go in a little bit more mathematical detail. So this is how RIS is treated from a communication perspective. So you have a base station here, excuse me, a RIS and several users. The RIS is controllable in terms of the phase. So each of the elements has a controllable phase, which means that the signal received at the user would be the transmitted signal, the channel from the base station to the RIS control, and then the channel from the RIS to the user. And then by optimizing this omega, you can maximize the end-to-end SNR. And again, the most common use case is to overcome line-of-sight blockage. When the line-of-sight pad is also there, the model is just extended like this. Now, let's now look at how RIS can be treated from a point of localization. When you have localization, you care about the parameters in the channels. You care about what are the geometric parameters in the channel HBR and HRU. And if you look into more detail, for instance, the channel from the base station to the REES, if you have line of sight only propagation, you would have a steering vector, which depends on the angle of departure, the channel gain, and then a steering vector at the REES, which depends on the angle of arrival. And now, if you know where the base station and the REES are, both of those angles are a priori known, so you don't need to estimate them. On the other hand, the angle of departure from the REES to the user is an unknown parameter, and you should estimate them using model-based signal processing. All right, so now what are some of the use cases for REES? I think the really attractive use cases there are these kind of almost intractable positioning problems. Just like we had with the single base station positioning, if you think about single base station positioning, you would think it would not be possible, but then we show when you add multipath, it becomes possible. And now since REES is a kind of controllable multipath, then it should also help to support single base station localization. So here is an example of how REES helps to solve problems that are otherwise not solvable. So you have a base station here, a REES and a user. You have two propagation paths, and then each of the propagation paths provides you a delay, so then you can compute the time of arrival. And now the nice thing with the REES is you can modulate the REES over time to have different beams over time, and this allows you to compute the angle of departure from the REES to the user. So remember before we said we could solve the single base station localization problem if the base station and the user had multiple antennas. Now you can even do it when the user and the base station has only one antenna. Okay, and the reason is that the time difference of arrival measurements gives you a hyperbola, and the angle of departure measurements from the REES gives you a line, and the intersection of the line and hyperbola gives you 1 point. So this is how you can localize yourself in SISO with help of a REES. And there, if you want to know more details, I refer to those papers. You can even now do this when the line of sight is blocked with help of a REES by using the near field propagation. So by using wavefront curvature, you can localize the user even when the line of sight is blocked. And some papers about this you can find here. And then you can go even one step further and take away the base station. And now the localization really becomes a sensing problem. So when the user is transmitting a signal and operating in full duplex, it can look at the backscattered signal from the REES and estimate the time of arrival, just like it would do with any other target. But since the REES is shining in a predictable way, kind of flickering, it can separate this target from any of the other targets. It can then also estimate the angle of departure from the REES to itself. And this constrains the user to lie on a sphere around the REES through the time measurements, and then a line through the angle of departure measurement. So that means you can localize the user even if it has a single antenna with help of a REES. And then you can find more information in this paper. As an example of how this could work in practice, I will skip this, is here a demonstration that we did at Chalmers using basically a millimeter wave array where we loop back the receiver to the transmitter, so it acts like a REES. And then we have here a base station antenna and a user device antenna. The base station is just illuminating the two REES, and the REES are sending sequential directional beams. And the user is measuring the total signal strength. So what the user is basically seeing is just measuring signal strength, and at some point when both of the REES are pointing toward the user, the signal strength will be really high. And that's what we're showing on the picture here. So we're showing the estimated and true position of the user by the different beams, and you see that the directional beams toward the user are the ones where the signal strength is the highest, so that tells us where the user is. So by using just simple directional beams, you can estimate the user with an error of about 10 centimeters here. And this is using a relatively small REES, of course in a small deployment environment. If you work with large REES in a larger deployment environment, you can get better performance. If you want to know more, we have this paper on arXiv with all the details of this paper. All right, this brings me to the end of my presentation. Also, my voice is almost gone, so it's good. So I hope now that you realize that radio signals have good potential to provide location information. They have always done this since 2G, but now as we go towards 5G and 6G, they really start to shine. The reason is that we have high frequencies where large bandwidths are available with many antenna elements that are being used, and then we get high angle and delay resolution. In 5G millimeter wave, there's still a lot of untapped potential that I talk about. This includes single anchor positioning, signal shaping, and sensing. Beyond 5G, lots of potential for AI, for REES to boost and enable localization. Many things I didn't talk about, for instance, that we need flexible signals and methods to deal with the flexible requirements. At some point, we are probably going to operate in the same band with similar parameters as automotive radar, and the question is then will be competing with them, or will it be one system? Hardware limitations will be really important for positioning and sensing, and I think this provides very interesting research area. And then also we should be modest and apply the tools and techniques from our connected research fields, such as satellite navigation, functional safety, synthetic aperture radar, non-Euclidean optimization, and so forth. There are many unanswered questions, so all the work I presented here uses very simple geometric models. Having good channel models that cover a variety of frequencies is really important. Having good hardware models that reflect different frequencies is also important. And then questions about how can we meet all of the requirements at the same time, right? How can we have at the same time high accuracy with low latency and have good coverage? This is a very hard problem. But of course, having lots of problems is really good because it's provided us with lots of opportunities. And I always say that since I think the introduction of research into 6G, that the golden age of radio-based positioning and sensing has begun. With that, I want to also acknowledge many of my collaborators. Here is just a subset of them, Gonzalo Seco Granados in particular, I've been working with for many years. And you can follow our work on the HexX and Rise6G website, as well as on YouTube and my personal website. And finally, I want to also acknowledge funding from the European Commission, from Vinnova, the Sweden Innovation Agency, the Wallenberg Foundation, the Swedish Research Council, and the Marie Curie Actions. And this ends my presentation. Thank you.
Okay, thank you, Henk. Very comprehensive overview on radio sensing and localization. So we have received a number of questions from our audiences. I think the first one was asked by Ahmed and Nima. So Ahmed, can you please unmute yourself and ask the question?
Yes, thanks, Fan, and thanks for the nice talk. I have just basic questions here about the localization accuracy, like in terms of position and orientation. So we always talk about the accuracy. There is a position, that means there is a point. But how this should be defined in relation to the object shape and size? And the second part of this question also related to the accuracy. So depending on the techniques, how to do to get the performance metric, because sometimes the localization accuracy also depends on the location of the object or the terminal under localization as well as the deployment. Thanks.
Yeah, so regarding the first question, so the relation to the point that you estimate and the shape and the size of the object. So here my answer would be that the position refers to the antenna array. You have a phase center of the antenna array, and that's the position that you estimate. And that position needs to be related to the physical object itself. The same goes for the orientation. So there's a default orientation of the antenna array, and then you measure orientation with respect to the default orientation. So it's really the antenna array that determines the reference for position orientation. And then regarding the second question, it is true that location accuracy or location performance in general depends on where you are. Right? If you're closer to the base stations, maybe things get better because you have high SNR. If you're further away or all the base stations are aligned, performance is worse. And this is why performance accuracy is not just one number, but it's a CDF, right? So you have a CDF of location accuracies, and then you care about the 99 percentile or 90 percentile that you have a good coverage. And this is, I think, similar to communication, where, okay, users have different communication quality depending on where they are.
Thank you.
Thank you.
Okay, so we have another questioner, Rainer Tolman. Can you please unmute yourself? And you can ask question to Henk.
I mean, my chat was mostly a remark, but it could also be turned in a question. My impression is that people very often do not clearly enough distinguish, if you talk about localization, that they do not clearly enough distinguish between emitter localization and radar localization. I mean, all that 3GPP stuff is emitter localization for cooperative signals. I mean, for signals that are very well defined within one existing system. So that is the most cooperative case that you can think. But I mean, my understanding is that sensing in general, or sensing is when we talk about sensing in terms of ICAS, we have a much more general view. I mean, radar is more general since in that case, the object does not, I mean, it needs only to be there and reflect waves. It does not need to cooperate. And even if we talk about emitter localization of non-cooperative objects, I mean, that could also be interesting application. Yes. I mean, it looks a little bit like military or something like that, but for critical infrastructure protection and all those things, there might be many applications. So, I mean, that was a comment, but I'm asking Henk for your opinion for that, let's say, classification of terms.
Yeah, I fully agree. No, I fully agree. And I think, yeah, that there's passive localization, that there's device-free localization, emitter localization, cooperative, non-cooperative. Yeah, I fully agree. I didn't want to be so correct here to start making all of those separations. But yeah, it's a whole field. And I think what is localization and not, because I think in radar sensing, a lot of the problems are also localizing targets, right? So, yeah.
Okay, thank you. That makes me happy.
I agree. Okay, I'm happy to make you happy.
And I mean, the consequences that accuracy parameters can almost not be compared between this, or error sources can almost not be compared with the three cases. Yeah.
Definitely, yeah. But I think here I talk about cooperative, active emitter localization. Yeah. Thank you.
Okay, thank you. And we have, I think we have time for final question, which will be asked by Yifeng Xiong. So Yifeng, can you please unmute yourself?
Oh yeah, Hank, thank you for the brilliant presentation. I'm aware that there's some power allocations as a source of resource allocation for joint localization and communication. So what do you think that we should consider if we design waveforms for both localization and communication? Do you think there's some good waveform that suit for both, or there should be some trade-off between them? Thank you.
By waveform, you mean like OFDM versus DFT spread OFDM or OTFS, or you're talking more about how to optimize the waveform, like the OFDM parameters?
Yeah, more sort of like waveform parameters, like the patterns in OFDM.
Right. So I think what is being done now in the standard is something that makes a lot of sense, is where you spend some time for positioning and some time for communication. And the reason is that the rate of change, the time scales are very different, right? You don't need to do positioning every millisecond. Things don't move that fast. You spend a little bit of time having optimized positioning signals, and then the rest of the time you use optimized communication signals. They don't need to be the same waveform at the same time. And that I think is different from kind of monostatic radar sensing, where you can use the same waveform at the same time. And then it makes sense to play those games and do those trade-offs. But for positioning, I don't think it makes sense.
Right,
you just do them at different times.
Okay, we still have many questions, but due to the time limits, maybe the questioners can send their questions to Henk by email. Right, Henk? Yeah. Okay, sure. So with that, I would like to thank Professor Henk Wymeersch again for his wonderful talk on integrated sensing, localization, and communication. So let's welcome our next speaker. So let me share my screen. Okay, so our next speaker will be Professor Fabiola Colone, who received the laureate degree in telecommunications engineering and a PhD degree in remote sensing, both from Sapienza University of Rome, Italy. And she was a visiting scientist at the University College London, and she's currently a full professor at the Sapienza University of Rome. So the majority of Dr. Colone's research activity is devoted to radar systems and signal processing. And she has been involved in research projects funded by the European Commission, European Defense Agency, Italian Space Agency, and Italian Ministry of Research, and many, many radar ICT companies. And her research has been reported in over 160 publications. And she's also the co-editor of the book, Radar Countermeasures for Unmanned Aerial Vehicles. And she has been the co-recipient of the 2018 Premium Award for Best Paper in IET Radar Sonar and Navigation. And since 2017, she's a member of the Board of Governors of the IEEE ISS, and in which she has served as Vice President for Member Services, and she's the Editor-in-Chief for the IEEE ISS QEB newsletters. She's IEEE Senior Member and a member of the IEEE ISS Radar System Panel from 2019. And she was Associate Editor for the IEEE TSP, and also a member of the Editor Board of the International Journal of Electronics and Communications. She served in the organization committee and in TPC of many international conferences, and she was a TPC co-chair of the IEEE 2021 Radar Conference, and is the TPC co-chair of the European Radar Conference 2022. Okay, with that, without further ado, let's welcome Professor Fabiola Colone. So Fabiola, please, the screen is yours.
Okay, can you see my screen?
Yes, perfect.
Okay, let me hide a few. Okay, so thank you very much, Fan, for your kind introduction. And hello, everyone. Thank you for being here today attending this webinar, and in particular, my talk that is aimed to provide an overview of findings and recent developments in the field of passive radar. But before starting, I would like to acknowledge all the members of my research group, the Radar Remote Sensing and Navigation Group at Sapienza University of Rome, without whom none of the results reported in this talk would have been possible. So this is the outline of my talk. Firstly, I will illustrate the basic architecture and processing scheme that are required for a passive radar to be effective. And then I will show some results from different surveillance applications. Then I will discuss the current trends of passive radar research. And finally, I will draw some conclusions. So when introducing passive radar to the radar community, this is usually referred to as a particular bistatic radar that exploits an existing transmitter as illuminator of opportunity to perform the typical target radar tasks of target detection and localization, and even advanced tasks such as target imaging or classification, all based on a receive-only passive system. And this brings in a number of advantages from the radar point of view, which are the low cost, no additional demand of spectrum resources, limited environmental impact, and also low vulnerability to electronic countermeasures. However, based on the same identical description, this system can be also regarded as a pioneering form of integrated communication and sensing, in which the sensing component is totally subject to the design, development, and implementation of the communication component. And in this regard, I believe it is very important to look at the results obtained in the field of passive radar, because this might be inspiring for many of the activities running in the field of ISAC. Well, the idea of passive radar is not new, as it actually dates back to 1935, when one of the first experiments, called the Daventry experiment, was performed in the UK in order to demonstrate the feasibility of a technology that would have been later known as radar. So in that experiment, they exploited a BBC transmitter at shortwave to detect an aircraft bomber that was flying in the proximity of the receiver, with actually very good results. But after the Second World War, the attention of the radar community was mostly focused on the more convenient monostatic radar, while passive radar had seen a renewed interest since the 80s, mostly driven by the need to react to the increasing congestion of the electromagnetic spectrum caused by the proliferation of several communication services. And since then, a number of papers appeared in the technical literature addressing the exploitation of different transmitters and for different applications. So the most exploited illuminators are for sure those of the broadcast services, for both radio and television, which are typically exploited for long-range surveillance applications, such as the aerial or the maritime surveillance applications. But more recently, the attention has been moved towards shorter range surveillance applications, such as against drones, but also vehicular targets and even people. Obviously, in such cases, this is accomplished by exploiting the higher frequency and wider bandwidth signals that are typically provided by the base stations for networking, but also satellite transmitters. So since my background is in radar topics, in this talk, I will mostly address the defense and surveillance applications of these systems. And in particular, I will focus on the first radar tasks of target detection and localization. So when dealing with surveillance applications, the main challenge is to provide a wide and continuous coverage with high reliability. And in passive radar, this translates into the need to detect the weak target echoes against both noise and the strong interference caused by both the transmitter of opportunity and other potential transmitters operating in the same frequency band. And this in turn sets strong requirements on both the employed receivers that should be able to manage wide dynamic ranges and on the signal processing techniques. So in this scheme, I have summarized the main processing blocks that are required for a passive radar to be effective. I will not go into the details of each block. However, I will try to provide some hints, some guidelines to the design of the techniques to be implemented at each block. So for sure, the most important block is the evaluation of the cross-ambiguity function, which is basically implementing a bank of cross-correlators between the surveillance signal, so the signal collected by the main antenna that hopefully collects the echoes from the targets, and Doppler shifted replicas of the so-called reference signal. This signal is assumed to be a good copy of the transmitted signal and is typically collected by means of a dedicated antenna that is pointed towards the transmitter of opportunity. So if that is the case, this block is basically implementing a bank of matched filters tuned at different Doppler frequencies, and this provides as output the typical range Doppler map where the presence of a target is detected is seen as a strong peak. So depending on the application, this block might be characterized by a very high computational load, which might prevent its real-time implementation. So therefore, several approaches have been devised to reduce the computational complexity by resorting to appropriate approximations. Among those approaches, the batches algorithm operates by fragmenting the signals into batches, and if the batches are short enough, the phase term compensation within each batch can be neglected, so that just a simple cross-correlation has to be evaluated on a batch-to-batch basis between the surveillance and the reference signal. The results of these operations are then fast-Fourier transformed in order to synthesize the Doppler dimension, thus obtaining the desired range Doppler map. As is apparent, this approach is very well suited for digital waveforms, since such waveforms have usually an inherent framed structure that can be exploited to identify the best way to fragment them into batches. In addition, I would like to highlight that this approach somehow restores the paradigm of a pulsed radar, where a range compression is first performed against pulses, followed by a Doppler processing. And we further observe that such range compression can be efficiently evaluated in the frequency domain, and depending on the considered application, the conventional matched filter can be replaced by alternative compression filters if a limited signal-to-noise ratio loss can be accepted. For instance, a reciprocal filter can be exploited with the aim to mitigate the effects of the waveform of opportunity by properly equalizing the employed signal spectrum. As an example, these figures show the output of the range compression stage for an OFDM signal, specifically in this case a DVB-T signal was employed, for a single point-like scatterer when a matched filter on the left or a reciprocal filter on the right are used. So at the price of a limited SNR loss, in this case it's just a few dBs, the reciprocal filter offers the capability to limit the side lobes level in the observed output, which is expected to be a strategic advantage in highly cluttered scenarios. And in addition, since it equalizes the power spectrum of the signal of opportunity, it makes the output almost independent of the exploited waveform, with additional benefits that will be discussed later in this talk. So going back to our processing scheme, regardless of the adopted algorithm for the evaluation of this block, when addressing the evaluation of the range Doppler map, one important message is to exploit long coherent integration times, because typically the power level of the employed transmitter is not adequate to guarantee the desired coverage. But on the other hand, most of the illuminators of opportunity that are typically used provide a persistent illumination of the observed scene. And we might certainly assume that the target of interest changes much slowly than the communication content. Therefore, a passive radar has the chance to coherently integrate the energy of the target echo for very long times, provided that accurate phase synchronization is guaranteed at the receiver, and if we are able to handle the very high computational load that this requires, especially in fast-moving scenarios, where also the capability to compensate for range and Doppler migration effects might be required, since these are caused by the movement of the target itself. So even exploiting very long integration times, it might happen that the target echo could be still masked by the side lobes of the ambiguity function, as these are caused by the strongest contributions appearing in the range Doppler map, which are typically due to the direct signal coming from the transmitter, as well as by its multiple replicas. Therefore, this block has to be preceded by a dedicated disturbance cancellation block, which is aimed to mitigate such effects. And as regards this block, it is important to observe that it cannot rely on typical clutter cancellation techniques usually employed in active pulsed radar, because such techniques rely on the assumption that the scene is illuminated by identical pulses, identical signal fragments, which in this case is not true, as we need to deal with time-varying waveforms. So ad hoc techniques must be designed in order to be able to adapt to both the observed scene and the exploited waveform of opportunity. And this in turn requires a good knowledge of the transmitted signal, as well as usual, a very high computational load. Actually, the requirements on the cancellation stage could be mitigated if we exploit signals that are characterized by ambiguity functions with extremely low side lobes, or if the reference signal is properly mismatched in order to remove the dependency of the ambiguity function on the information content. And for instance, this is obtained by substituting the matched filter with a reciprocal filtering strategy, as I mentioned previously in my talk. So the signal processing scheme also includes some signal conditioning blocks, which perform transmitter-specific conditioning of the signals aimed at improving the ambiguity function or at providing high-quality filtering. And after all these stages, the final map obtained is sent as input to a conventional detection stage, which allows to detect the strongest peaks appearing now in the map, while controlling the false alarm rate. All the detections are then finally sent in input to the tracking stage, which provides a filtering of the obtained measurements, together with the capability of removing isolated detections, which are likely to correspond to false alarms. So with this basic signal processing architecture, the performance of a passive radar might be still limited. First of all, we might notice that with a single surveillance antenna, the targets are only localized in the range Doppler domain, since we do not have any information about their direction of arrival. But most importantly, I should mention that with this approach, the performance is largely dependent on the employed waveform of opportunity and on the instantaneous characteristics of the propagation channel. And both these effects are highly time varying. So in order to improve the performance of the passive radar and to make it robust with respect to the time varying characteristics of the scenario, we have considered the possibility of exploiting some information diversity in different domains. For sure, the spatial diversity is an asset, and this can be obviously implemented by exploiting multiple antenna elements on receive, which in turn provides also the capability to measure the angle of arrival of the target echo and to localize it in local Cartesian coordinates. But also, spatial diversity might include the possibility of exploiting multiple nodes distributed across the area to be surveyed. And this is expected to further improve the localization capability of the system. But this also requires good synchronization among the different nodes, as well as the possibility of associating the measurements provided by different nodes under very different bistatic geometries. Another domain in which diversity might be obtained is the frequency domain, and this is inherently offered by several transmitters of opportunity, which emit their signals at different carrier frequencies, typically to serve different sets of users. While these signals are intended to carry different information contents for the users, from the sensing point of view, they just offer different possibilities to sense the same identical scene. So they can be fruitfully combined in order to improve the sensing capability of the system. Similarly, the polarization diversity might be exploited again as offered by transmitters of opportunity, which are able to emit their signals in different polarizations, for example, vertical and horizontal. But also in this case, polarization diversity might be synthesized on receive by exploiting orthogonally polarized antennas in order to collect the signals at the two polarizations and make the system robust with respect to the conditions of the channel. So different signal processing architectures can be considered to exploit fruitfully this diversity of information conveyed in different domains. A very simple approach is offered by this cascaded architecture, where the signals collected at different channels, either spatial channels or frequency channels or polarimetric channels, are firstly separately processed according to a basic passive radar processing scheme, and then a multi-channel target detection can be exploited to jointly exploit the different outputs obtained at different channels. Alternatively, an integrated architecture can be considered where the diversity of information can be exploited at each stage of the processing chain to improve the interference removal, the integration of target energy, as well as its detection and localization. So some of these approaches have been used in the experimental results that I'm going to show, which where this first example was obtained for an experimental passive radar prototype that was developed at Sapienza University of Rome. It exploits FM radio signals as waveforms of opportunity, and it has been mostly used for air traffic surveillance applications around the area of Rome. In this test, specifically, the transmitter of opportunity was located about 35 kilometers from the receiver site. The surveillance antenna was pointed in order to cover the air traffic departing or landing to the Fiumicino airport in Rome. And the passive radar exploited a quad channel receiver, which provided digital down conversion of up to 4 FM radio channels from each physical input. Also, we employed dual polarized antennas in order to simultaneously collect the vertical and horizontal polarized versions of both the reference and surveillance antennas. So in this case, we were able to test for the exploitation of both polarization diversity, frequency diversity, or their joint combination. So in these first two figures, The gray lines report the available air truth for the air traffic in the area, while the black dots represent the results of a passive radar collected across time, so over 50 consecutive data files. So the results are reported on the by static range velocity domain, and as it is apparent, when using single polarization, figure on the left is for the horizontal, figure on the right is for the vertical polarization, the detection performance is highly varying. In this case, the vertical polarization provides slightly better results, but I can say that this is not always the case, because in other examples, in other tests, the horizontal polarization seemed to be preferred. And the joint exploitation of the signals collected at both the vertical and horizontal polarization certainly allows to enhance significantly the detection capability. For both targets in the first 100 kilometers by static range, but also it allows to detect additional target tracks that are not detected by the single polarization operation, and this is a clear result that shows how this approach is able to extend the coverage of the system, in this case up to 150 kilometers. So further improvements are obtained when jointly exploiting the signals collected at different polarization and different carrier frequencies. And this is quite apparent in this second test. In this case, the black lines are the air truth, while the red dots are the results of the passive radar. This first figure is for the case of a single frequency, single pole operation. If we separately exploit the frequency diversity or the polarization diversity, we are certainly able to improve the performance with respect to the single frequency, single pole case. However, when jointly exploiting all the available information, in this case, 4 FM radio channels were combined together with the 2 vertical and horizontal polarizations, we are able to further extend the coverage of the system to up to 200 kilometers and further improve the continuity of detections guaranteed for targets flying at shorter distances. So thanks to the wide data set available, we were able to quantify the benefits from different approaches, and the details are reported in these papers listed here for your convenience. I will move to a second example of experimental results that have been obtained for an experimental campaign that we have conducted in cooperation with the colleagues of the Leonardo company, which is one of the most important radar companies in Italy, using their AULOS system, which is basically a dual band passive radar operating in both the VHF and the UHF bands. Specifically in this case, I will focus on the results obtained for a DVB-T-based passive radar, so a passive radar that exploits OFDM signals of opportunity. So the tests were conducted in a military airport in Pratica di Mare, using a transmitter of opportunity that was located about 30 kilometers far away from the receiver site. Several tests were conducted against both the air traffic of opportunity to demonstrate the long-range surveillance capability of the system, but also additional tests have been conducted to demonstrate the capability of protecting the airport area against the threats carried by commercial drones. So in all these tests, we have simultaneously collected the signals from 2 different DVB-T channels, and 3 antennas were employed on receive with different spacing, so as to synthesize a kind of non-uniform linear array. So in this case, we had the chance to test for both spatial diversity and frequency diversity, and again, their combinations. So I think these are the most interesting results to show, the ones obtained against the 2 drones. So in these slides, I am reporting the results obtained for 2 different tests. The first test, figure on the left, is for a case where the drones flew at a maximum distance of 1.7 kilometers from the receiver. The second test is for a larger distance, up to 3 kilometers from the receiver, which was basically the limiting area of the airport surface. In both figures, the continuous line report the GPS-based air truth for the two drones in green and red respectively, while the dots are the results of the passive radar, which in this case are mapped into the local Cartesian coordinates thanks to the availability of the angle of arrival information for the detected targets. And as you might observe, the figure on the left clearly showed the capability of continuously detecting the two drones along their tracks, and also a reasonably good capability of localizing them in the airport surface. But in contrast, the performance degrades in the second test, where the targets flew at a larger distance, so obviously the signal-to-noise ratio is reduced and the accuracy in positioning reduces accordingly. So in this case, however, we are exploiting just one of the two available DVB-T channels and only a pair of surveillance antennas, which were displayed at a distance that was larger than half the wavelength, which also explains these ambiguous plots arising here, which corresponds to mispositioning of some of the detected targets due to the limited, non-ambiguous angular sector that can be obtained with this setup. So in this case, we try to exploit this diversity of information conveyed by the two DVB-T channels together with the three available surveillance antenna arranged in a non-uniform linear array layout. So I can go back and move on again in order to let you appreciate the improvement, both in terms of detection capability, but mostly important in terms of localization accuracy obtained with this approach. And also the misposition, the plots have been removed and properly localized thanks to this spatial diversity and frequency diversity. So actually we are kind of using a frequency diverse array offered by the different transmissions at different carrier frequencies. So I want to recall that here we are talking about very small drones that were flying 3 kilometers far away from the receiver side. So we think that this was a very good result. And it's nice here to watch the movie that we have recorded during the entire acquisition, where we can clearly see the capability of the system to continuously track the two drones. What's interesting in this movie is that together with the tracks of the two drones colored in this case, we also have several additional tracks in gray. Maybe you can appreciate them in this movie. And these were associated to the presence of several birds flying over the airport area. And this in turn highlights the need for advanced radar tasks to be accomplished, which deal with the capability of classifying the detected threats. So also very interesting in this case is the fact that with the same data, just changing the parameters of the signal processing, we were able to offer a long-range surveillance against air traffic by being able to detect aircraft up to 200 kilometers from the receiver. And this is not a trivial result in the radar world, because typically these tasks are accomplished by very different radar systems, while in this case we are exploiting a single passive receiver to obtain simultaneously both the short range and the long range surveillance capabilities. And similar considerations also apply to another test that was performed with the same system, the Leonardo Aulos system, for a maritime surveillance application. So in this case, on the left, the results for a short-range surveillance against a small boat, a rubber boat, that was detected at up to 3 kilometers from the receiver, while on the right, the results obtained for a long-range surveillance applications against big ships and cargos that were detected at 200 by static kilometers from the receiver, which can be easily evaluated to be beyond the standard radio horizon, and this reveals some over-the-horizon capability of such systems when operating at low carrier frequencies. So, well, in this considered applications, so for both aerial and maritime surveillance applications, passive radar has certainly reached the point of maturity with several prototypes and systems already available in the market. However, the question is, which are the current trends in passive radar nowadays? So I've tried to list in this slide some of the main aspects that are being investigated in the field of passive radar. They include the exploitation of satellite transmitters, the possibility of installing a passive radar on board of moving platforms, the joint exploitation of passive radar techniques together with device-based passive sensing, and the implementation of dense networks of low-cost sensors. So in the following, I will briefly address these aspects by providing some preliminary results that have been obtained by our research group at Sapienza. So as regards the satellite transmitters, we need to mention that this brings in a number of strategic advantages which motivate their use. So this makes available an extremely high number of illuminators of opportunity, thus covering possibly any given point on the Earth's surface, even areas that are not covered by ground transmitters, for example, in the open sea. And this also allows a number of potential applications, such as the protection of infrastructures with low vulnerability, the synthetic aperture radar imaging, and others. So obviously, there are several challenges that have to be faced when exploiting a satellite transmitter. First of all, the very low power density available on the Earth's surface, and this especially applies for the case when geostationary satellites are exploited, since those are thousands of kilometers away from the Earth's surface. Also, the need to track the satellites might be an issue when instead satellites in the medium and low Earth orbit are exploited. So here I'm showing the setup that we have used to preliminarily demonstrate the feasibility of a DVB-S satellite-based passive radar in the KU band. We have exploited a parabolic reflector to collect the reference signal from the transmitter, the satellite transmitter, while just a feed horn was used to provide the wider angular coverage that was needed at the surveillance channel. So these are some examples of detection results reported over the range Doppler plane. The first one is for vehicular targets that were detected up to the limits of the parking area where the test was performed, so up to hundreds of meters. In this case, and okay, the second test is for people moving in the parking area that could be correctly detected at up to 100 meters approximately. Okay, well, in this case, you can certainly observe the spreading of the detection in the Doppler dimensions that are caused by the moving target, and these were mostly recognized to be due to the micro-Doppler effects generated by the body parts of these targets. Also, we performed some tests against drones using very small drones that were detected at tens of meters from the receiver. And this was a very surprising result from our side, because I recall that in this case, we are using a geostationary satellite that is 36,000 kilometers away from the observed scene, and this clearly reveals the potential applications of this approach. So when addressing the possibility of having passive radar on board of moving platforms, again, there are a number of strategic advantages in this approach. In fact, it might offer covert and low-cost monitoring of wide areas, and this can be also an easy deployable surveillance system. For example, if we think about installing a passive radar on board of a UAV, for example. Again, there are specific challenges that need to be faced in this application. The most important ones are the size and weight of the system, especially when small platforms are considered, but also the impact that the platform motion has on the passive radar operation. And among these effects, for sure, the need to recover the reference signal from the moving platform might be a challenging issue, but also the fact that even the stationary scene will appear as Doppler spread due to the platform motion. And this spread in the Doppler dimension will cause several slowly moving target echoes to be totally masked by the returns of the stationary scene. Now, in this case, as well known in the radar literature, we can exploit multiple antenna elements on receive to implement space-time adaptive processing techniques. However, as for the basic signal processing scheme, it is important to mention that conventional stop approaches that are usually exploited in active systems cannot be straightforwardly applied to the passive radar case, because we need to deal with the fact that the waveform is changing from fragment to fragment. So in other words, not only the scene might be changing, but also the signal itself. So we need to cope with these aspects and design appropriate techniques to be robust to this effect. So this is what we try to do, and we have preliminary tested the approaches that we have proposed against the data set provided by the colleagues at the Fraunhofer Institute, FHR, in Bamberg, in Germany, where they performed an experiment using a ground vehicle as moving platform. The passive radar featured 4 receiving channels installed on the trailer of the ground vehicle. In this case, you might see on the left the results obtained when using a single antenna on receive, and you can clearly observe the widening in the Doppler dimension of the strongest returns due to the stationary scene, which basically mask all these targets that were present in this scenario. But after the application of the proposed approach, the figure on the right, we can verify the good cancellation capability of this technique that is able to mitigate the clutter returns and to preserve the echoes from the moving target, thus allowing their detection. So before moving to the next point, I think it is worth making some considerations about the possible applications of passive radar on board of moving platforms. Among them, I would like to mention its potentialities as autonomous driving assistance system. In fact, it is well known that when active radar units are used on board of vehicles, the mutual interference might be a major safety concern, especially in very congested areas. Actually, several techniques have been devised to overcome this problem in the field of automotive radar. Now, the passive radar concept inherently eliminates the problem of mutual interference, since it allows different radar units to share the same transmitted signal. So the exploited source might be a third-party non-cooperative transmitter as well as a dedicated signal. And considering this advantage together with the additional benefits of reduced costs, reduced energy consumption, I think that there might be interest in using a passive radar in automotive applications, at least as a backup system. And if we combine this concept with the idea of exploiting satellite transmitters, it is clear that this can be also used in rural areas where such transmitter might provide their persistent illumination. So the next point in my talk is the joint exploitation of the passive radar principle together with a device-based passive sensing. I really like the discussion in the chat related to these two techniques, and I totally agree with the classification that have been proposed. So the approach of jointly exploiting these two techniques is very useful when the targets of interest can be assumed to carry a device that emits its signal in the same band of the passive radar. And this is because the same passive receiver might be exploited for both techniques. This is, for example, the case of Wi-Fi signals. So we can detect people or drones based on the passive radar principle, so detecting their echoes, their backscattered signals stimulated by the emissions of the access point, that is in this case our transmitter of opportunity, but also simultaneously we can exploit their own emissions that are due to Wi-Fi ready devices carried by these targets in order to localize or to provide additional measurements for their localization. So in this case, I'm reporting some results for a Wi-Fi based passive radar developed at Sapienza University of Rome. So on the left, the movie of the test performed, where two people were moving across each other, while on the right, I'm reporting the results of the localization provided by the passive radar only. So in this case, the passive radar standalone was able to correctly localize the two targets based on the backscattered signals from their bodies and discriminate the two targets since they are correctly distinguished in the range and Doppler domains. But this is not always the case. So if we look at the different tests, the situation might change. So in this case, the two people start the test by moving close to each other, and the resolution offered by the system is not sufficient to discriminate their presence, the presence of the two targets, until one of them changes its direction and is discriminated in both range and mostly Doppler domains. So this test reveals some limitations in the passive radar approach, especially with reference to this short range application. The first one is the resolution capability that can be addressed by designing wider bandwidth signals, but also the fact that when our target is stationary because it stops to change its direction, the passive radar is not able to detect it because it will be removed together with the returns from the stationary scene. So in order to mitigate these effects, we try to jointly exploit the passive radar principle together with a device-based passive sensing. So exploiting the measurements that are provided by a passive emitter localization. These are reported for these two tests as red plots in these figures. The first test is for a person that was moving on this triangular trajectory and stops at each of its corners. Again, these red plots represents the results of the localization obtained by exploiting the packets that its smartphone emits in order to connect to the access point, while the blue markers report the results obtained for the passive radar that instead exploits the reflections of the signals emitted, in this case by the access point, on the body of the target itself. What we might notice is that when combining the two measurements, so the track reported as green in this figure, we can obtain increased detection capability with additional continuity, because the target can be detected both when moving and also when it is stationary, and also an improved capability in terms of localization accuracy. It is important to notice that the smartphone, the device, the Wi-Fi device, typically transmits many packets when the target is stationary. So when the passive radar is not able to detect the target, because it is likely that it is trying to connect to the internet or downloading some files while the person was stationary. So I think that there is a lot of complementarity between these two technologies that should be exploited jointly in order to improve the performance. And a similar approach was also exploited in this second test against a drone that was transmitting the video that was recorded during the test to a remote control. And again, we reported in red the results of the localization obtained using that signal emitted by the drone, and in blue the results of a passive radar. The green track is finally the one obtained when combining at a tracking stage with an appropriate technique the measurements provided by the two techniques. And again, this allows the best results both in terms of detection capability and localization accuracy. So moving to the last point considering in this talk, the implementation of a dense network of low-cost sensors. So a possible strategy to limit the complexity and thus the cost of each node within a network is, for example, to relax the requirements on the availability of a reference signal in passive radar. In fact, I recall that the passive radar architecture and signal processing scheme that I have introduced at the beginning of my talk rely on the fundamental assumption that a reference signal is available, as it is needed for both disturbance cancellation and cross-ambiguity evaluation. Specifically, this signal is usually collected via a dedicated wireless or even a wired link connected to an additional receiving channel. And I want to highlight that this receiving channel should be of very high quality, because the reference signal has to be a good copy of the transmitted signal, but also because it constitutes a reference for time, frequency, and phase synchronization at the receiver. And all this yields non-negligible implementation costs. So if we aim at reducing the complexity of the receiver, the reference channel should be removed, and alternative strategies could be considered to recover this reference signal. And this is especially true when digital transmissions are used. So one possibility is to reconstruct the reference signal from the surveillance signal itself by demodulating and remodulating again the signals collected at the single channel according to the transmission standard. And this obviously requires a perfect knowledge of the transmission standard. Alternatively, a priori known fragments of the transmitted signal can be exploited as those used by the communication component in order to accomplish some synchronization tasks. This last approach offers an interesting link of passive radar processing schemes with the so-called CSI, channel state information-based approaches that are usually employed in Wi-Fi sensing. In fact, if we recall that this cross-ambiguity evaluation can be decomposed into the cascade of a range compression stage followed by a subsequent Doppler processing, and if we assume that a reciprocal filter is exploited based on a priori known signal fragments at the range compression stage, we can easily show that this stage is basically implemented a conventional channel estimation, which is the first step required by a CSI-based approach. And then the output of this channel state estimation can be sent as input to the Doppler processing in order to analyze, to study the moving sources in the environment. So this interpretation shows that the passive radar processing scheme somehow generalizes the CSI-based approach used in Wi-Fi sensing. On another topic, I want to highlight that regardless of the employed recovery strategy for the reference signal, if a reference receiving channel is not available, some issues might arise due to the signal mismatch in the reconstruction of the signal that might lead to SNR losses. Also, when exploiting known fragments of the signal, this might bring some losses due to the fact that only a portion of the received signals is exploited. So we are inherently limiting the integrated energy. But in addition, some other losses might arise due to a non-perfect synchronization in time, frequency, and phase. And a significant effort should be made to recover the synchronization, but this is possible only in the presence of a strong direct signal component in the surveillance channel. So if all these effects cannot be mitigated, and if the loss experienced are unacceptable, we could make a very different choice and resort to a reference-free signal processing scheme. So a possible strategy is to exploit a non-coherent processing scheme where the presence of a target is detected by extracting the amplitude, the modulation that it produces on the direct signal coming from the transmitter. This approach neglects totally the phase information and only requires a very simple processing scheme, which encompasses an envelope detector followed by a low pass and downsampling stage, the removal of the zero frequency component, which is likely to correspond to the returns from the stationary scene, and a short time Fourier transform, which yields as output the typical spectrogram where the target motion is mapped into a Doppler signature that allows its detection and tracking. So this approach has been optimized for a Wi-Fi sensing system in the framework of a research project funded by Huawei. Here I'm showing the experimental results obtained in a test where a small drone was used as cooperative target. So the figure on the left showed the movie recorded during the acquisition. I'm going to start the movie, while the figure on the right reports the results obtained in the spectrogram built for the recorded data. So as it is apparent, I don't know if you can see this small drone flying in the area, we are able to detect its presence in the spectrogram as it yields this very clear Doppler signature here. We might notice that when the drone approaches the transmitter receiver baseline, the velocity measured decreases while its Doppler increases, its velocity increases as far as it moves away from the transmitter receiver baseline. In any case, we might notice that the drone can be continuously detected even when it is outside from the recorded area in the movie. And this example shows that a reference-free approach guarantees a good coverage of the considered area. But most importantly, I would like to highlight that we are exploiting the amplitude information only of the surveillance signal. Therefore, this approach is inherently relaxing the requirements on the receiver setup, since it does not need a dedicated channel to collect the reference signal, and it does not require phase or frequency synchronization. It only needs a rough temporal synchronization in order to fruitfully combine the measurements that are provided by different nodes when available. This approach has been also exploited against signals of opportunity in the VHF and UHF bands, specifically FM and radio and DVB-T transmissions. In this case, aiming at a wider coverage, the proposed approach was demonstrated to be effective only at very extreme bistatic angles, namely when the target crosses the baseline between the transmitter and the receiver, thanks to the forward scatter principle. And in addition, we observed that the exploited waveform has a non-negligible impact on the performance. Here I am reporting an example against simulated data for the same test for an FM radio transmission and a DVB-T transmission, and we might see that very different results are obtained. This is not only due to the change in the carrier frequency, which is responsible of the narrower response in the DVB-T case, but also it depends on the employed modulation. Specifically, the OFDM waveforms was demonstrated to yield this increased background against which the targets compete to be detected. So we have designed ad hoc techniques to mitigate these effects, and we have extensively tested them against experimental data. Here I'm just showing an example for a test performed on the roof of our faculty. The transmitter of opportunity was located 36 kilometers away from the receiver, and the system was tested for the detection of aircraft landing to the Ciampino airport in Rome. Such aircraft along their path crossed the receiver transmitter baseline, thus yielding a V-shaped signature in the Doppler time domain, as shown in this figure, that reports the available air truth. So if we directly apply a conventional reference-free signal processing scheme, the result is quite limited, as the target can be only discriminated at very low frequencies. In other words, when it exactly crosses the baseline. In contrast, with the proposed approach, that takes into account the employed modulation, much better results are obtained, thus extending the area where the reference-free approach is effective. Now, the proposed approach based on the passive radar principle makes available a dense network of transmitters of opportunity, but in addition, since it limits the complexity of the receiver node, it potentially allows to deploy a large number of sensors where each sensor can operate in a standalone mode without setting strong requirements on the synchronization and data transfer between the different nodes. Therefore, I believe that this could be an effective approach to be used for wide area monitoring or in many civilian applications where the use of complex and very expensive radar systems, active radar systems, is basically prevented. So concluding, passive radar has reached the point of maturity in several surveillance applications, and further developments are being made in innovative scenarios. Indeed, the research activity on passive radar has addressed and proposed the solutions for a number of issues that are expected also to be present in ISAC systems. So when the sensing and the communication components have to coexist. However, it is also expected that the flexibility provided by a joint design of two components might yield enhanced capabilities and also widen the range of uses. So this concludes my talk, and thank you very much for your attention.
So we have received a number of questions in the chat, and I think the first question was asked by again by Rina Thoma. So Rina, can you please unmute yourself?
Yeah, thank you very much, Fabiola, at first for your presentation. I mean, I like the comparison to passive coherent or passive radar, passive coherent localization and much, since integrated communication sensing per se can be very close, except that it is cooperative, and passive radar normally is not cooperative between transmitter and receiver. But my question is a little bit more specific. In one of your early slides, I mean, I do not know exactly, around 10 or so, you compared the matched filter response to the inverse filter response, and your matched filter response did show some spikes. So I mean, my impression was that those spikes may result, yeah, I did one, may result from the cyclic prefix in the DVB-T OFDM signal, yeah? So yes, if you would have removed the cyclic prefix, it would disappear, yeah?
Okay, you're totally right. So the peaks appearing here are due to some periodicity appearing in the waveform. In this case, for example, the cyclical prefix, but also the pilot tones that are responsible for periodical structures in the OFDM signal. So for sure, one possibility is to mismatch the reference signal by removing those contributions in the signal in order to control. So actually, in that case, it's not more a matched filter. It's like a kind of mismatched filter, but not that much. The problem is here, I want to highlight this additional problem, which is very important, I think, that whichever is the approach, even if we are able to remove those peaks, the main problem of a matched filter or similar matched filter is the fact that the output is dependent on the information content. So not only those peaks are a problem, but also all these side lobes, because they are varying with time. So if we consider different fragments of the data, we will see different outputs at that stage. And this is a real problem when we want to perform some cancellation, because we rely on the fact that the waveform is identical and only the scene might change. But this is not the case when dealing with non-cooperative waveforms, because their information content is in the change. So there is the real content, the real information for the communication component, while the passive radar has some big issues with this problem, with this aspect, because it is not able to remove perfectly the stationary scene since it is changing. The illumination is changing actually, not the scene.
Yeah.
So that's
I
why.
completely agree. Yeah.
Sorry.
I completely agree. I mean, passive radar per se is normally thought to be non-cooperative. But if you are an integrated system, I mean, in case of integrated communication and sensing, integrated sensor and transmitter, so we can act in a cooperative way. And then we can do all this stuff. We need that cooperation in that case, or we can take advantage of this cooperation. Okay,
yes,
thank you.
Least. You're welcome. Thank you for your question.
Okay, thank you. So our next question was from Ahmed Bazi. So Ahmed, can you please ask the question by yourself?
Yes, thank you, Professor Fabiola, for the interesting talk. I just have a small question regarding the performances in slide 26. You mentioned non-uniform linear arrays in your configuration. Do you think the antenna array geometry plays a role in the performances, or is it independent of the geometry being used? Thank you.
So in this case, the performance was largely depending on the layout we exploited for the antenna setup. So here there is a picture of the antenna setup, and exploited 3 antenna elements displayed according to a non-uniform linear array that was needed in order to extend the non-ambiguous angular sector that would have been obtained if using a uniform linear displacement among the different elements. And this is a typical strategy adopted in passive radar, because one of the main characteristics of such systems is the low cost. So we want to keep very low the cost in order for these systems to be competitive with respect to their active counterparts. So the idea is to exploit few channels, but if we extend the aperture of the antenna with 2 or 3 just elements, obviously we suffer from large angular ambiguities. While if we exploit a non-uniform linear array, we are able to offer larger apertures by exploiting only few antenna elements. But this is not only the only strategy adopted here, because we have also exploited it together with the frequency diversity. So this is actually not only a non-uniform linear array, but a frequency diverse array, because in the DVB-T band we have a very wide band exploited for the transmissions of different channels. So we exploited the channels emitted at very different carrier frequencies that basically offer different wavelengths. And this allows to see the same array as 2 different systems with different spacing. And this provided additional diversity to be exploited for the localization capability, as mentioned in these slides. And this provided the improvement that I've shown in the slides. I don't know if this answers your question.
Yes, yes. Thank you very much, Professor.
Okay, thank you. So we have another question from Professor Da-Qing Zhang. So he's asking about setting of the Wi-Fi. So please, Professor Zhang.
Yeah, thanks, Fabiola, for your insightful talk. And actually, my question is regarding the, you have shown 2 demos using the Wi-Fi, for tracking, right? Basically, you were talking about the, combining the device-based and the device-free, basically the passive radar approach. Actually, in this demo, how did you, place the Wi-Fi devices?
So you are referring to these 2 tests?
Yeah, the previous one. Just now you show actually, yes, this one.
Okay.
You just show the video and where, you have 1 person, walking around, and then 2 person, right? And then they walk in different directions, right?
Yeah, so the position of the exploited nodes is reported in this figure on the right. So we have
how many
we have
devices?
just two nodes, two receiving nodes, one access point. One of the two nodes was mounted in a quasi-monostatic configuration, so it's very close to the access point antenna and is equipped with a couple of antenna elements on receive. The other node instead is displayed by several meters with respect to this node and only includes features one antenna element. So basically for this localization results, we have combined angle of arrival measurements and time difference of arrival, or better, by static ranges provided by the two passive radar nodes in order to obtain the localization capability in the XY domain.
But in this case, you are not using the commodity Wi-Fi devices, right? Are you using the commodity Wi-Fi devices, or you are using specialized?
We are using a receiver that is based on COTS hardware components, but is especially intended to implement the passive radar operations, so signal processing scheme. Is this what you mean?
Yes, it's just the commodity Wi-Fi devices with 5G or 2.4G gigahertz.
So you mean that, are you asking about the transmitter or the receivers?
Both. Basically, they are using the same.
So the transmitter is a commercial Wi-Fi access point that is used in our houses. So it's a very simple one. And in particular, we are operating in this case at 2.4 gigahertz.
Okay.
Okay. While the receivers are ad hoc receivers based on commercial off-the-shelf hardware, but they have been developed by our group at Sapienza, because we use them in order to record the data and then process them offline to demonstrate the capability of the passive radar. So we are not using.
But how many antennas? How many antennas are you using in the receiver side?
At the receiver side, we have this first node that is equipped with two antennas on receive, just two antennas, while the second node is only equipped with a single antenna. So in this case, the association is performed in the bistatic domain, and then we combine the angle of arrival information provided by this node and the bistatic range provided by this node together with the bistatic range provided by the second node. So we have three measurements to solve the bidimensional localization problem. And this is what we have done. We have okay.
How about the other ones? The next slide, you have you are using both passive radar and
yeah.
In this case, what's the setting for the devices?
Sorry, can you repeat your question?
So in this case, what kind of transmitter and receivers are you using?
This is basically the same setup, totally the same setup, with the only difference that also the second node is equipped with two antenna elements on receive, and none of them is mounted in a monostatic configuration. So both the two receiving nodes are implementing a bistatic geometry. So here we have the transmitter of opportunity, the Wi-Fi access point, and the two nodes that provide jointly both angular measurements on the detected echoes, but also bistatic range measurements. So in this case, when exploiting the emissions from the device, we obtain this red curve, these red plots here. They are not very accurate because they are based on very few packets emitted by the source, while the passive radar allows a much better localization because it takes advantage from a longer integration times across the multiple packets emitted by the access point.
All right. So in this case, how far is the person away from the devices?
It's on this graph, so it's about 40 meters at the nearest point, and it reaches almost 70 meters at the farthest point.
You mean for the Wi-Fi devices, right?
Yes,
You mean
the devices are
you mean
here.
the Wi-Fi devices can sense the person who is actually 50 meters away?
So this triangular trajectory is the trajectory of the target. So this graph is reported in local Cartesian coordinates. The nodes are here, you see, at 0, 0 coordinates, while the target is moving at a minimum distance of 40 meters from the receiver, and even more during its trajectory, during its motion.
All right. In this case, also the person is carrying a device, right?
Yes, it's a smartphone.
Okay, thank you. Yeah, thank you very much.
Welcome.
Yeah.
Okay, thanks, Professor Zhang. So I think we have a final question, a very quick question from Mohammed Bazi, please. So you can unmute yourself.
Yes, so following the discussion with Professor Fabiola and Professor Zhang, I just have a very small question. In the demo that you showed where the two people, the two men were walking and then one separates, one of the nodes have two antennas only, you said. And that's where you do angle of, that's where the AUA estimation is done. My question is, are you doing such a good job in AUA estimation only with two antennas? Or maybe am I missing something? Thank you.
Because we are good. We are very good. No. So
yeah.
actually, the fact is that I want to recall this point, which is very important. In radar, in sensing, the idea is not to exploit the information in the signal. So you can integrate energy. You can integrate the echoes from the target. That's why we can gain the required energy needed to improve the accuracy in the localization. So if I had to understand the content of a packet, I need to have a very high signal to noise ratio at each single sample of that packet. But in sensing, I have a the challenging issue of detecting and localizing the weak target echoes. But on the bright side, I have the capability of integrating their echoes, their energy coming from their echoes. And this allows for a better, much better localization capability. Also, these results can be improved by a subsequent tracking stage that was not performed here, just to show the accuracy obtained with the raw measurements, but additional information might be used about the considered targets to drive a tracking stage in order to filter the measurements.
Okay, thank you very much. Thank you.
Welcome.
Okay, thanks, Hamad. And I think, so obviously our audiences are highly interested in your demos, right, Fabiola? So yeah, so
I'm happy about that.
yeah. So if anyone of our audiences have further questions, please send emails to our speakers, and then they'll be happy to answer. Okay, so with that, I would like to thank Henk and Fabiola again for being here as our guest speakers, and we hope to host your talks in our future events. Okay, so with that, I would like to conclude our seminars, and I hope all of you have a very good, happy summer holidays. And stay tuned, we will have our next season of the Wymeersch series from the, let's see, from the September to October. Okay, goodbye.
Thank you. Thank you. Bye-bye.
Bye.
Bye-bye.
Bye-bye. Bye.